what I'm going to talk today is about the MeanFieldType games. And this is, people have been looking at control of Markov systems. So with one controller, typically. And this framework is when you have two controllers or more. Okay? So in that context, you end up into games. Because now you have two interacting controllers, and one controller could be the central planner, and the other one could be just a jammer, somebody who is not necessarily going in the same direction as the central planner. So game theory is back again to, in this context, instead of control problem, you have control problem with more than two controllers, and you can write down Nash equilibrium and so on. So that's the underlying idea behind this thing. So it's a joint work with several people from different groups. So I would like to acknowledge them here. Konyozu from one of my colleagues at New York University. Jiangao and Yidashu are my PhD students. Mikhail Masa and Yudan are my postdocs. And my former advisors and collaborators. So Altman, Tamer was here yesterday, and Jean-Yves from EPFL, Alain, Walem, and Dario. So those are the main collaborators of this work here. And I do appreciate support from the US Air Force, especially Jean-Luc, who is here, supporting this work. And for that being said, so we have been discussing a lot about games. So this is not relevant anymore today, but since I made this slide, those are old slides, but I think if some of you came yesterday, it's still interesting. So a game is given by a set of participants to the game, so players, agents, and so on. Each of them has a choice space to make. There's a set of actions, and then there is a preference for each of those actions. Usually what we do in games is that we try to order those preferences. And if you can order, there is some order in the mathematical sense, you can show that there is a function that characterizes those preferences. So if you cannot order, it's unclear. Okay? So in this talk, I am assuming that that function exists so that I simplify my life. So this is particular class of games. Okay? So there is a certain objective function, and you are interested in this function. Each person is interested in his function. If those functions are identical, this is what we call common interest games, because the objective is common. If they are not identical, well, you might end up to more complicated situation. So Nash equilibrium points. So we're discussing about how to change the actions simultaneously. So you can write down simultaneous deviation. You change two components instead of just one. You could do that. We call it two-strong equilibrium. If you change three components simultaneously here in the optimization, three-strong equilibrium, and so on. The issue is you might end up with something that is that might not exist at all because you are asking a lot of properties to the equilibrium. So here is limited to the unilateral deviation case. So it says that player J cannot improve his, here I'm maximizing, so cannot improve his payoff by unilateral deviation. There is a small difference here. Your choice might be coupled with the choice of the other. This is typically something that happens when you have constraint problems. Okay, you can choose, but within a certain restriction. Okay, you are part of a community, a society, so you can do whatever you want, but not exactly. It should be constrained in some cases. So that's what we call generalized Nash equilibrium or constrained Nash equilibrium and so on. And this goes back to a lot of reference. So in the game theory literature, especially in evolutionary games, we have large population of players, and this transition to the limit people have been using it in genetics by Fisher, and mainly by the evolutionary game theory by Hamilton and so on. So, and then the next step is to add a state. And this was already done by Shapley, who was from UCLA here, who introduced a Markov Games with the transition probability. So you can move from one state to another according to some transition kernel. And we was interested in the discounted long-term payoff. Okay, so that's the work by Shapley. Now, what we do next is to add here a distribution of state or action, or both together. Okay, so your objective function depends not only on those terms, but also on the distribution of it. When you do that, you get a non-von Neumann utility function, because it's not expected the simple expected value. Okay, that makes a small difference. So with the non-von Neumann utility function, your optimality equation are a bit going to change, and this is what will happen in MeanFieldType Games. Okay, so now I am back to the introduction of MeanField Games with large population of players. This is a very old slide. Sorry for those who are not acknowledged here. But still, I think it's interesting to introduce this. So for infinite number of players, continuum or not, but infinite, there have been a lot of previous discussions about populations and so on, especially in the Volterra. You can look at that one. It's very interesting work with large population of players models in the population context. Population dynamics context. And then another one that is very relevant is the watt drop in the traffic flow. You have large number of vehicles over the roads, and you are interested in traffic equilibria with infinite number of players. Traffic equilibria. So this was introduced by watt drop. We have seen the kinetic equilibria yesterday. So this one is traffic equilibria. Okay. You can see them as a static MeanField game, and it's coincide with this steady-state MeanField game equilibrium, because they have a consistency check there as well. And then the continuum of players models by Robert Aumann and co-authors. And another work I want to highlight here is the one by Dubé. So this one is about aggregative games. If you look at most of the talks here, they have interaction model, right? And the interaction model comes through some aggregative structure, right? And this work is about aggregative games. So a game model where the payoff function depends on your own decisions and state and an aggregative term. So that's what we call aggregative games. And you can see asymptotics of aggregative games to get MeanField games, and they've been looking at that type of scenario. And then for dynamic games, so those are static, if you want. And for discrete time, or discrete state, here I'm unclear. So it's discrete time for most of them, but some of the work are, especially the one by Jogo, are not discrete time, but discrete state. So Jovanovic is one of the first reference I've seen on backward-forward equilibrium in the equilibrium setting. That's why I most of the time cite this person. Backward-forward equilibrium means there is Bellman equation and there is Kolmogorov equation together in in the same work. Okay, that's why I'm highlighting it here. And then extension of it by the same author and his co-advisor, Rosenthal. And extension of that work by Berkins and Bernard. This one does have common noise. In economics, we call it global uncertainty. It doesn't have the same name, of course, right? Global uncertainty. So there is an uncertainty that is external that's influencing the entire distribution of the players here in that work, okay? And then population dynamics, asymptotics when n goes to infinity can be found in the Weibull and so on. So that's for discrete time. Now, for continuous time, I jump over. Some of the references I'm pointing out here are not probably the earlier. I apologize for that. But so Brownian, one of the closest literature to MeanField games, and then the work by Mini, Peter, and Roland, and then Lasserie and Lyons, and the work by Cornelius and Kurt is close enough to that framework. And most of the previous studies on convergence, I get inspiration actually from here, that work. So let's talk about assumptions. So in all these papers, we assume this indistinguishability between classes. Okay? And if you look at carefully in the literature, in the probability literature, for example, they go beyond this. They have indistinguishability, pairwise indistinguishability, three-wise indistinguishability, four-wise indistinguishability, and so on. And they have already shown convergence to measure and so on. So the theory has more results are available in this direction. Well, large number of agents that we have been discussing here, and irregularity assumptions. So MeanFieldType game, what it does is to take a Markov-Vlasov equation and look at when you have two or more number of decision makers, controllers. Okay? The payoff function depends on the state, actions, and a distribution of states. For this talk, let's discuss only on the distribution of states. And there is a transition kernel. Well, the states will be dynamic, so there will be some movement in the states. So basically, this is what we call MeanFieldType game structure. Now, there is an interest on doing this. The first thing is you look at not only the expected value of your payoff, but the variance. Go beyond. So look at the second order term, the variance of your payoff. If you look at the variance of your payoff, there might be some interest about it because it's talk about risk, and people are really sensitive to this type of thing, especially in finance. Okay? If you are sensitive to the risk, you need to look at large deviations, and you need to look at this type of thing. So if you optimize the variance of your payoff, then it's a natural framework for MeanFieldType games you end up. So I have a scenario where I just want to minimize the variance of my own state, just that. Okay? So for those who are doing MeanField games, what we do is expected value of x minus expected value of x. X is now the payoff. In MeanField games, what we do is we go and we freeze this. Let's assume that the expected value, the second one, is fixed. Freeze this, and then optimize with using stochastic control. But if the state is my own state, then when I change my control, I'm changing my own state. So I'm changing the expected value. If I do that, I cannot fix it. I cannot freeze it. Okay, so that's the underlying idea about MeanFieldType games. So that's one is MeanFieldType control, but you can have some coefficients and different controllers. So the agenda today is to talk about these aggregative games. There is a motivation behind it, and I will explain a couple of slides on it. And I'll be talking about dynamic programming principle for this problem, stochastic maximum principle, and then discuss about the risk-sensitive version of the problem. The last part of the talk will be on how to solve the system and approximation techniques. So for MeanFieldType control, there is a huge literature already. So one of the main reference is this one. So there is the work by Bogdan, Gage, Lee, and Peng is about the limiting approach for MeanFieldType problems. So control of Markov-Vlasov, and when the size of the system goes to infinity, what happens, and so on. And then optimization is involved in the paper here for problems that were of this type. Okay. minimizing the variance type of problems. So that's why most of the papers are functional of the expected value. There is a reason for that. Okay, it's started from here. This one, and then you can understand that there is a more interest in this field. So we have been doing through maximum principle most of these papers, and recently we are back to the dynamic programming in infinite dimension, and these papers are discussing about the connection between the two, and I will talk about those connections here in the rate-sensitive case. Okay, this is the setup. Simple class of aggregative games. So the payoff function, as I said, depends on your T is for time, S for state, aggregative term, some aggregation. Here I'm not considering a state localized dependent, but this is a simple structure, and the action, and there is the S-tint is for regimes. You have different regimes, and you switch from one regime to another. That's the S-tint, and the S is the standard state. So the state solve is a stochastic differential equation of Markov type. So this is the drift. It has the same aggregation structure, but the function might be different. So in this term, you might have the second moment. Here you might have the mean, here you might have the third moment, whatever type of structure you want to do. Okay? And then this is the diffusion coefficient. This is the Poisson jump. We have been discussing that yesterday in the meeting. So we have a Poisson jump process, and the rate of the jump is given by gamma, and the other term is the switching rate. So you switch from, and there is a finite number of switch. This part is finite number of states you could switch. So when you change your switching here, S-tint, you move from one dynamical system into another because they are function of the switching. You can choose different functions. Okay, so compared to the classical literature, what we have added is those two terms. Okay. Now, does it change really the problem? We will see that actually it doesn't change that much, except if you want to get interesting results, because this term will bring an integral of the value function in the dynamic programming. This one brings another averaging, as in the classical finite case. So averaging of the value, integral of the value, if you want to do numerics, for example. Okay, so that's the setup. But since I'm choosing aggregative terms here, these aggregative terms are in finite dimension. I'm mapping it into, so all this is in 1D, one dimension, let's say, one dimension, and this is returning a real value, for example. Okay, so phi is one dimension. I'm returning a real value, so I can do, because it is in finite dimension, I can get maximum principle in finite dimension. I mean, the processes are much simpler than controlling a measure. Here we will not be controlling a measure, thanks to this aggregative structure.
So could you explain again the switching mechanism?
So this is a Poisson jump process with the rate that is given by gamma. So it means that your state is here, directly it can jump to another one with a certain rate. Right. So we want to explain, those are noises, normal Brownians. If you want to do bigger jumps, you cannot explain through this. The bigger jumps happens here. Some jumps are very huge, and some are much smaller. This is for smaller jumps, and this is for a very big jump. The last one is for switching. You change from one dynamical system into another dynamical system. This is what we call hybrid or whatever.
These are exogenous. These aren't controlled in any way?
The rate, you see that the rate depends on, is the classical. So the rate depends on actions, on MeanField, and state, and time as well.
Okay, so the rates are controlled.
Yeah.
Okay.
So through that, you control everything. Okay. So that's the setup. Yes.
What is the intuition behind putting the control in the volatility?
Very interesting question.
What is the intuition?
So
what kind of problem are you thinking?
So if let's take basic example. When the state is just your revenue, okay, you have SDE for the revenue. This is very common in finance, for example. So if it is the revenue, you know that the revenue, the noise, your state appears in the volatility term because it's geometric Brownian or so on. So that's one of the, but your action influences the state. So indirectly, you have a function of your action there as well. It's indirectly a function of the control. Okay, so that's one of the motivation we do this. But if you don't like it, you just remove the actions here, and we have examples of that type. Okay?
Do you have some dynamics for S here?
So S-tinned, the dynamics for S-tinned is hidden in this martingale. So S-tinned is a switching process. It has this rate delta. And the associated martingale, here we centralize, we normalize. You could see I'm putting tint. It means it's central, centered. The associated martingale to the switching is this M tint. So you switch up or down through this rate here, and there is really a probability of switching probability associated to it that I will explain next. There is a transition probability for it. Okay? Any other question on this? If you understand the model, everything else is just there. I've been reading it, and I copy-paste them, and you'll see that actually is. Okay? So we consider this setup. The first part is cooperative. Cooperative means they jointly optimize. Collectively, they maximize this. The second part is non-cooperative. Everyone is optimizing its own structure. Okay? And sometimes we consider risk sensitive, so from the talk yesterday, so risk sensitive payoff instead of the risk neutral one. So if theta I goes to 0, I keep the same notation as Tamer. So when theta I goes to 0, this becomes the expected value of the payoff. But when theta I is strictly positive, this is risk seeking person. If theta I is negative, it's a risk averse person. Okay, you can have different sensitivity with respect to the risk. So then the key thing is Ito's formula. Okay, so I don't need to reinvent anything for this. I just look at in the literature, and those are well-established results. It's a really very well-known thing. So you take the function of the state and the switching. This S-tinned is for the switching. I need that. Because it's appearing in my payoff function. And this first term, those are the standard Ito. And then there is a jump term, and there is a switching term. The jump term comes with integrals, because we are taking Poisson jumps. Okay? And the switching term, well, it's normal switching. So this is the question of Mini. So there is a transition probability for the switching, of course. And this is the normal. So when you switch with a certain rate. So that's adding to the state. There is a modification here, as here. Okay? To the state, you add the rate. Okay? So those are well-established results. Now we take this. Then we get our Fourierplank and our Hamilton-Jacobi-Bellman equation. Okay? So here we go. For the Fourierplank, you define the adjoint operator as in the classical sense. It's just the integral as the integral and of f and j as the inner product, and the adjoint operator is defined that way. And if you do this, you can automatically get the Fourierplank equation. So this is the law of S, starting from M naught. Okay? So the difference with the literature is this term and this extra term, because we added those in the model. So we get a jump term in the Fourierplank equation and the switching term. This is the small change in the model. But it's important to add this, because if you have models with larger jumps, this term is really important. It captures it. Okay? Now, this is Fourierplank. Let's see the Hamilton-Jacobi-Bellman equation. For that, since I'm in MeanFieldType regime, The difficulty there is you need a appropriate state to have a Markov type of thing. So everything will be now in infinite dimension. The new state is what was established here. That's the new state of my system. And I convert all the payoff function to be expected, as I'm doing here. Okay? Expected payoff, terminal one, and the instantaneous payoff. Now you want to optimize this. Okay? So you transform the original problem into a Markovian problem, but now it's deterministic. I don't have external common noise to that. Deterministic, and dynamic programming does apply to this problem. There is no thing. I have a state that is deterministic, control problem that is deterministic, so I apply dynamic programming to it. Copy paste. Okay? So this is what I have done, and the dynamic programming equation becomes this. There is a difference. The value function, I need this. This makes a difference with the classical literature. In general, we have the gradient and the second derivative, right? Now the entire function enters into the Bellman equation. And here is how it looks like. This is the Meltonian. Okay, so the reward function, the classical one, the gradient term, the second order term, then you have a jump term, and then a switching term. Okay, J is for jump, and ST is for switching. I couldn't call S because the state was S. Okay, sorry for that. So this is switching, this is for jump, and the rest is classical. Okay, that's the changes. Now, this equation is not easy to handle it, this one. We take the derivative of this in S. S is the state. Okay? We differentiate this, and this is what Alain called dual functions, because it's a derivative with respect to M in the Gatto derivative sense, or Fréchet. In any case, we are going to assume that it's all regular, so they will probably coincide. So we take the derivative with respect to M, and we call this small v. Small v is not the value function. It's the derivative of the value function. Okay? Derivative in the measure sense, and that solves this equation. The difference now is that there is an extra term here. So for problems that are mean-field free, means independent on the mean field, this disappears, and this function is exactly the value function. But if you are mean-field dependent, then this is still there. Okay? Now, we differentiate this function small v using the Ito's formula. That's why I told you that the Ito's formula is the key, because after I'm using that again and again, there is no innovation here. Okay? We just apply Ito's formula, with now this term appears. Okay? That's the only change in the Ito's formula. So this is the Ito's formula for MeanFieldType issues. And I'm going to compute this for our aggregative structure, because most of the applications we are looking at comes with aggregative structure. I didn't see anything so far that is not in aggregative form. So we are going to consider this. This is one particular aggregative structure, but aggregative structure of this form, and then differentiate it. So this is the derivative of this one with respect to M. There is phi that is going out. If you differentiate again to get the Weissenstein derivative, you need to differentiate this in S, and you get phi S. Okay? And this is what we are going to do. And we identify the correspondence between the stochastic maximum principle. From here, you could see the coefficients, right? So those, we call them P, Q, R, S, and so on. This is similar to Francois' talk, the Y and Z. Y and Z are now P and Q. Okay, that's the only change. So P will be this one, see? But for the derivative of the small v, means the dual function. So that is P, and then this is Q. So that is like Y and Z, if you want. And R is for the Poisson jumps, and S is for the switching. Okay? That's for the switching, that's for the Poisson jumps. And then there is second order adjoint processes. For those who are familiar with stochastic maximum principle, first order, as in classical optimization, first order is not enough to say that it's the maximum or the minimum, right? You need to go to second order if the Asian is positive and so on. Right, so this is what we do. So we go to second order adjoint equation, second derivative. So P bar, Q bar, R bar, S bar. For each player, you do that. Okay? Next, I introduce the Hamiltonian. So the Hamiltonian function is the classical Hamiltonian here plus the one that is coming from Poisson jumps and the one that are coming from switching. There is a switching term, there is Poisson jump. This is how the Hamiltonian is modified. This term here and this term here. Now, you differentiate this in S in the state, and then you get the first order adjoint processes. And the only change in the classical literature is this term. But since we are working in MeanField, this alpha has expected value. I have probably forgotten somewhere. Expected value of H hidden somewhere. And this is for the terminal, you see, this is extra term. So because of the aggregative structure, there is no derivative in M here. There is just a derivative with respect to the third component. So this is finite dimensional. This is in finite dimension. There is no derivative with respect to measure that is needed. That's why we are looking at this problem. Okay. If you work in the aggregative term, then you get something that is in finite dimension, and that's maybe easier to work with. Okay? That's the idea. So all the function phi's are supposed to return something that is a vector or just a real number in this case. 5 minutes? Okay. Now, once we establish these results, then we are interested in the system. Is there any solution? We are going to impose a lot of assumptions on it because we are not able to do in general case. And the assumptions are that everything is smooth and everything is bounded. It doesn't exist, but there are cases like arc tangent as the drift. Those are bounded. We are able to do something there. And for the second order and so on. This is the main results. So the optimality, if there is an equilibrium, then it should satisfy this equation. Up to here, it's very well known in the stochastic control literature. Second order, with second order. When your diffusion coefficients are controlled, right? Now, this is for the jump term. This is for the switching term. It doesn't really change that much. Okay? Now, for uncontrolled jumps and uncontrolled diffusion, these two disappear, and you can still work with the optimizing the Hamiltonian. Okay? And to establish this type of results, so the system, if you look at carefully in the results by Francois, his talk, so we are assuming that this is bounded, and the coefficient, so all the coefficients that are written here are bounded. So I get a linear backward forward equation when I add the other one. But linear, because it's linear, when the coefficients are bounded, we can just use normal growth to show that there is a solution for this, because the coefficients are bounded and the system is linear. Okay, that's how we got those results. So some recent development on it. We have partial observation case for this model, one of the paper here. So this is with partial observation in the same setting with aggregative structure and so on. Okay. And the risk sensitive case is use the same techniques, and I think I will discuss just the example briefly. So we are able to solve this semi-explicit because we need to solve an ODE in the end that, as people do in Riccati equation, we stopped at that ODE. It's not completely explicit. So this is the action is bounded because I want to be very simple. This is the drift, okay? And this is the diffusion that is geometric, is you are multiplying by S, and same thing for the jump, okay? And this is the payoff function. So the payoff function depends on the switching, so the regime at which you are, and this is the terminal payoff. It has some MeanField term on it. The terminal payoff has a MeanField term, but just with a small perturbation of it, so that we can see how our solutions are dependent on the MeanField term. That's the main idea. and explicit solution for it. So we have an unsat. For V, this is the optimal control, the first one, optimal control, the second one for the second player, and the need to solve this ODE. It's an ODE, okay? So that's why I'm calling semi-explicit. We're able to show that the system here, this is completely independent on the rest. So this has a positive solution because the terminal is positive and it's linear. So this has a positive solution, and then we take that positive, plug it here, and show that this has a solution, and then this is the moment, so the alpha moment. And alpha is less than 1 in this case. We want concave. We are maximizing. Okay. I stop here.